Okay, so let's go to the second part. So we so far talked about very specific mechanisms for very specific kinds of data. So it was either this binary data or categorical, so to speak, but really this mechanism is only suitable for binary data that we described. And this other one for real value data, but you can think of arbitrary complicated data. And you would like to think about answering arbitrary queries to the database or to a system, yeah? So where should I go to get a good pizza, right? It's a very good query. How should I go to work? You know, get an answer back. So let's take the how should I go to work? Well, maybe there's a traffic jam right now, and there's data about the traffic jam, and it comes from people. And of course, people don't want people to be able to guess that they are somewhere in the city specifically, right? So in theory, right? There is a possibility that you could use data from where people have been to deduce something about their behavior, right? Classic example is Strava. Did you hear about this? Yeah, you did. So Strava is an application for running and stuff, and there were people that were running using Strava in a military base somewhere in the Middle East or something like Pakistan or wherever, and it has this feature where you have like an average activity of people in various regions, so they have paths, so you can know where it's nice to go jogging. But of course, you know, the location of this base is sensitive information. So even by aggregating data, you could kind of guess the location of a base. So, but you can also think about individual people being targeted through the average, through the release of statistics. Okay, but in general, we want to talk about interactive queries. So you want to say where should I go jogging, whatever. So you have some data X, okay, fixed data, so that doesn't change. The user asks some query, somebody asks a query, and the response to the system. Okay. Again, it could be that X is the historical data you have about your clients, okay, in the credit assignment. And Q is the specific data and credit that one particular person wants. So I want $1 million for 1 year, and this is my data. Okay, so this is the query of this person. And you respond with something, okay? And there is some common utility function. So here we might say that the utility function is, well, your utility function will depend on some model, right, in some sense. But basically tells you how much you would gain or how much somebody else would gain from you giving a specific response. Okay? So if you think about your own welfare, because you're the bank, you say, okay, given what I know, given my data, and given what's the utility if I give the money, what's the utility if I don't give the money. Very simple. You can think about it as the utility to somebody else, if you like. So a student is doing an application to the university, and I have lots of historical data from students, and I want to make a decision, should I admit a student or not. Maybe my welfare is also important, because I have kind of a fixed budget and from the government, and my only purpose is to educate students, so it's like how much will the student gain from being educated here, for example. So you may want to maximize this, for example. Okay? So you have some way of maximizing things, and one other idea, by the way, is like, take a simpler example, you want to report an average, okay? So the query is, what is the average? Okay? Data is X, your answer is a number. You could say, well, I will report something that should be close to the average, so I should have a utility function that increases when my answer is closer to the average. So for example, you could have that your answer is, okay, this doesn't quite work. That works. Sorry, this doesn't quite work. Doesn't matter. So you can say that your answer is basically has a utility that is maximizing average here, and you respond to this. Okay, that's so specific. U X A, and the query is implied to be the average, but doesn't matter. Okay, so let's wait for this. So your query is how exactly you want to minimize this error between your answer and the actual average. So depending on what power you raise, you might get different answers. So here, because you can always maximize this always to 0, the set is equal to that, the answer is the same no matter what Q is, right? But we would like, instead of just replying with the thing that maximizes utility, we would like to have an algorithm that not only maximizes utility, but also tries to be differentially private. Okay. So normally, if you had a differentially private, a non-differentially private algorithm, then this would be A star, which is the maximizing probability 1, okay, and some other A probability 0. So it will always be the action that you choose will always be the one that is maximizing utility, if you were not going to be differentially private. Because that's what you want to do. You want to maximize utility. So your probability distribution over the possible actions is singular. So there's only one possible action in this particular case, right? Yeah, you seem doubtful. So there is no false choice here, right? Always. The false choice is always to take A equal to that. Yeah. So you can define this as a probability distribution with 0 everywhere apart from one point, which is this point there. Okay. So but we know this cannot be differentially private because it's deterministic, so we would like to have a random mechanism. So there is a very simple one. It's called exponential mechanism. Okay, I want you to ignore this basic structure and just look at the basic of the formula. We just say that the probability of A given X is basically proportional to the exponential of epsilon times the utility of A for X. Okay. That's pretty nice. So let's write about this here. So under the exponential mechanism, the probability of taking an action A is basically proportional to the exponential of the utility of taking the action for data X. Okay. There's usually also a query argument, but we just simplify, we wouldn't ignore it. Let's say it's always the same query, what is the average? And for the question, what is the average, we can specify this utility function, right? Minus sum I xi divided by n minus a. Okay, so then that means that this p of ax is proportional to e epsilon okay, and this seems kind of something that we've seen before, right? This looks like the exponential, the Laplace mechanism, right? It's the same thing as the Laplace probability density function. And if you change this and say there's a q there, then you can have q equal 2 and then it's Gaussian or whatever. Right? So you can have a lot of different mechanisms just by changing the utility function for this one mechanism. Actually, most of the well-known mechanisms that exist can be formulated in terms of this exponential mechanism. And the nice thing about it is also you have a specific utility. You know, you care about this U, maximizing this U. Yeah. So it automatically tells you, okay, what's the way you can do it if you want to maximize a U. Now, the only difficulty is then when A has an infinite set of values, then you have this integral instead of a sum. But in some cases like this one, it's a non-distribution that you get, so the integral you don't really care about, because there's a closed form solution for the integral. So you end up sampling from what is basically a Gaussian or Laplace distribution. Okay, so that's the basic idea of what is the exponential mechanism. And let's see. So what do you think happens when we take epsilon to infinity for this mechanism? Okay, let's say that there are two values only. Yeah, let's make it easy. Say there are two actions only, and one has a higher utility than the other. So let's say one has a utility of 1 and the other has a utility of 0. Then what you get is, let's see what you get. So you have probability of A given X is E of epsilon, right? E of epsilon times 1 plus E of epsilon equals this, yeah. Times 0, right? So that's E of epsilon plus basically 1. Okay. So when it takes to infinity, then this becomes 1, right?
Yeah.
So you take this action with probability 1. When it becomes 0, then they're all the same, right?
Yeah.
So you take each one with equal probability. So basically, if you go back to what it says, when epsilon goes to infinity, then you don't care about privacy at all, or infinite privacy loss. You just maximize the utility, right? When you go to 0, then well, just random. So, okay. Again, the same choice. So what is the right choice of epsilon? It's a big problem, and there is a way to solve it. If you think about in terms of what is the practical level of accuracy you get from your algorithm, or what is the utility you really get. So how much utility are you willing to sacrifice? Yeah. This you can maybe more precisely formulate. So for a given epsilon, you can see how much utility you're going to can calculate from here. How much utility you are going to lose compared to actually maximizing the utility. So instead of selecting the epsilon beforehand, you can say, okay, well, there is this level of accuracy. I can increase the epsilon a little bit more and get higher accuracy if I want higher utility. So you have an acceptable level of utility, and then you tune your epsilon to just get exactly this acceptable level, which sometimes makes more sense, yeah, for practical applications. Yeah. If you think about the bank, for example, well, they would like to have at least not lose money, right? So you have some constraint like this. Okay. So let's see what else is here. So the last thing I want to mention is how you can use differential privacy to do completely different things than what I mentioned. Okay, so differential privacy is cool for privacy, but people have noticed that you can also use it to do other neat things. So in the first couple of weeks, we mentioned about adaptive data analysis, tuning your models to the data, estimating them on different data. So what the standard view is, you have a prior or model space, some training data, some holdout set, and you come with some posterior with some specific model from your models class, and then you measure the result on a holdout set. Yeah. And then you're supposed to basically stop there. Okay? But what happens usually is that you use again the same holdout set, get a new result, and so on. So you reuse the same holdout set lots of times. And does anybody know Kaggle? Yeah, so Kaggle is a machine learning competition where people submit their answers to different things. So how it works like this is you have your training data and there's a holdout set which you use, let's say, once a day to see how well you're performing. And you'd never see this data, you just test your algorithm there. But what happens most of the time is that people seem the best in this holdout set when they, at the end of the experiment, they test them on a completely new test set. They see that the top ones are not the top anymore. So they somehow learn this hidden holdout set. Yeah. So you can actually learn this hidden holdout set. So one way with which you can avoid this is to use differential privacy. Now this is kind of surprising, maybe, but think of it like this. Let's say I try classifier, an arbitrary classifier, on my holdout set data, yeah, and then I see for every example maybe whether I classified correctly or not. I don't really have to see the example. I just see for this example it has to classify them correctly or not. Okay. Then I basically, in the end, without actually seeing the examples, because I know how my classifier looks like, I can basically guess where the positive examples and where the negative examples are. If I have just a linear classifier, yeah, I can say, okay, all the examples there were 500 negative and 400 positive on the other side. If I change my classifier a bit more, then I see that there are 499 and 401. So there was an example there in between that I now misclassify, that I now classify correctly. Yeah. So now it seems like I know there's an example here. Yeah. So you don't know anything, so you have a classifier, and there are 500 examples here and 500 there. Yeah, but you know you have classified correctly. Fine. So this is your positive side and negative side. Okay. Now if you move there, then you can see that maybe you are losing now, so you have 499 and 501. So you know that there has to be an example here of the different label. Yeah. So you don't have to know anything about the data at all. So in theory, you could just learn dataset by just trying out different classifiers and seeing the result. Yeah. So what's the differential private solution to the problem? Well, instead of showing the result at any point, we just say, I measure my classifier's performance on the training data, and then I ask this query, how much more, or do I have significantly more error in the test set than in the training set? And then you get a differentially private response, not even yes or no directly, just a randomized response saying, well, yeah, but maybe not. Yeah. So, and actually this has been, what's going on? Okay. What I was saying, yeah. So basically, this is the algorithm. So you have some performance measure, some threshold, and you add some noise basically to the threshold. So then, whenever you see you don't reply yes or no, you have a noise threshold saying, well, is my test set result more than tau worse than the training set result? And then this guy adds some noise and says yes or no. So it can be true or false. And there was an experiment done published in Science, I think, where you had a classifier that was trained on a very high dimensional data set, which was all completely random. Okay? So two classes, 0 or 1, and let's say 1,000 features, all completely random. And of course, if you have a complicated enough model, then you can always perfectly learn the training data, even if it's just random. So in this case, it was just a linear model, actually. But because you have so many features, it's always easy to fit. So there is an example I can show you. So this one here. That's what I want to show for the end here today. So it's nice, you can play with this if you want. What happened here? Yeah. So this is pretty nice. So here you see the performance, the accuracy, right? If you just your training performance on the data, and this is your validation performance on the data. So these are all completely random, but somehow managed to fit both of them by doing parameter tuning. Yeah. And this is the performance you measure really on the completely hidden test data. Yeah. So training performance, holdout performance, and hidden test data performance. So here you're allowed to tune on the holdout if you want. Yes?
Is it kind of you choose a model like it's false positive, or like when you have just a linear regression with too many parameters, some are significant? Is it just like that? Or?
Yeah, it's exactly this. Yeah, it's a linear model basically, and they fit the parameters of the model by doing feature selection.
So it gets something that's significant by random, or it's good by random?
Yeah, yeah. It's just randomly good. And you can find the right feature so that you perform well also on the holdout set.
Yeah.
Because you can measure the performance in the holdout set. So you can remove some features, add some features, until you get good performance on the holdout set. You don't have to see the data, you just see the performance. And this is good enough. Yeah, okay? And then here, this is what you do if you have this adaptive holdout, or this differentially private holdout. You don't never see the performance in the holdout set. You just see this differentially private answer saying, okay, you are doing much worse or not much worse than training. And if you're doing much worse, then you don't want it. So you want to keep the case where you're doing more or less as well. Okay, but it does, by using this one, you can basically estimate. So basically, you can change this threshold tau. Say, okay, how much worse should I compare myself with? So you can compare yourself with 5% worse or 10% worse, and then for each one of these tau that you select, you get an answer. So you can test for various thresholds, and you can have some kind of average answer. So you see here, this line is much more, has a much higher error bars than here, of course, because this comes from these differentially private answers. But it's basically in agreement with the actual test data, right? So this is one thing that you can do with differential privacy. People have also used this for this exponential mechanism for games. So it's individual having a utility function, and then they all together need to come to some decision. So the problem is that a lot of times you lie strategically about what you want in order for you to gain more. So in a similar manner to this randomized response mechanism that kind of lets you tell the truth, the exponential mechanism also allows you to be more honest, so you can be approximately truthful in your responses. So you can apply this to auctions, for example, and things like that. And there are also very interesting links between differential privacy and learning theory. So learning algorithms suffer from generalization problems if they have too many parameters, but using differential privacy, you can basically guarantee stability of the algorithm and so on. You can also guarantee that they have good generalization ability. So these are kind of research directions, not part of the class, but I'm mentioning them to you because some of you might be interested. Okay, so I guess that's fine for basic stuff about what is differential privacy and stuff like that. And there's nothing more to say at this point.